Bismillahirrahmanirrahim. Today we will talk about the single value decomposition for MIMO channels. So this is lecture number 24 for week 11. So we talked about SVD decomposition in the previous lecture. Let's see how does it give an insight into MIMO channels, or does it help or not in reliable communication for the MIMO channel. So SVD can be employed as a tool for MIMO wireless systems and communications. The question is how. We saw that the MIMO channel matrix can be decomposed into these three matrices, where U is an orthonormal matrix which gives I, and when we do this operation, and V is the unitary matrix which has this property. Now this E matrix is a diagonal matrix containing non-negative singular values at the diagonal elements, and rest of the values are 0. Now consider a MIMO channel model in which we have received vector of R cross one dimension. H is a R cross T matrix. X vector is the transmit symbol vector with dimension of T cross 1, and W is a noise vector with R cross 1 dimension. So instead of having the direct channel matrix, let put H is equal to U into E into V Hermitian matrix, or the single value decomposition of this H matrix. So if you put the value of H matrix into the decomposed matrices, we get this equation: Y dash is equal to U into E into V Hermitian into X vector plus W vector. Now at the receiver side, multiply by U Hermitian. So whatever we get at the receiver, we multiply it with U Hermitian. That is, if you multiply U Hermitian with this matrix and open it up, you get this value: U Hermitian into U into E into V Hermitian into X vector plus U Hermitian into W. So as we already know that if you decompose H matrix into orthonormal vector matrix, you get I, because it has such properties. So Y tilde, this is basically a new vector at the receive end, would be diagonal matrix into V Hermitian X vector plus W tilde. So at the transmitter, perform this operation. This is called pre-coding. We know the channel matrix, we can pre-code it with V because we've already decomposed. So if you multiply your signals with this V matrix, you get a new symbol vector which is called X vector. So instead of transmitting X directly, multiply it with V. So now the received vector would be Y tilde would be equal to this value of diagonal matrix multiplied with VH, and what we have transmitted is we have transmitted now X bar, which is equal to V multiplied with X bar. We already know that V Hermitian into V, that is equal to I. So at the end of the day, Y tilde will be equal to the diagonal matrix multiplied with X tilde plus W tilde. So let's see into the dimension of these matrices. Y tilde would be a T cross 1 vector. E matrix would be T cross T. X tilde would be T cross 1, actual symbols that are transmitted, and we have T cross 1 noise vector. So what effectively it says that we have Y1 tilde, Y2 tilde, YT tilde received symbols, and we have a diagonal matrix with diagonal elements as such, and the transmitted symbol vector ranging from X1 tilde to XT tilde plus the noise vector. So if we open up these equations, because all these values are zeros, we will have a set of linear equations. All are basically multiplied with different singular values. Y1 tilde would be equal to sigma 1 x1 tilde plus w1 tilde. 2 yt tilde is equal to sigma t xt tilde plus wt tilde. So this is just a combination of t parallel channels. Okay, so we have parallel channels for each symbols that are being transmitted. So this set of equations, it is basically called spatial multiplexing. What we have done is spatially multiplexed the signals and send it virtually two independent parallel channels. So these are T parallel channels between Tx and Rx. So original channel was not multiplexed, it was mixed with each other. We have used the spatial domain and made the channels parallel to each other, sending each information separately to each separate channel. So this is a generic form of the spatial multiplexing, in which we have transmitted symbol for the ith channel, we get the received symbol on the ith channel. Now this is simply sigma I is the gain of the ith channel. So there are T parallel channels. We have T information symbols which can be transmitted in parallel. So this phenomena is called spatial multiplexing. What effectively we have done here, we have decoupled channels sigma I. So we have totally decoupled outputs. Why I mean decoupled? Because the channels are separate, they are parallel, they are not mixed with each other, they are not dependent on each other. So this is done because of the SVD decomposition and because of the diagonal matrix. Because the non-diagonal elements are giving the value of 0. So we have T streams of information. So what does it mean? At the same time and at the same frequency band, we are sending multiple symbols. So that is why it is called multiplexing. Spatial because we are sending into independent parallel channels in the spatial domain. So multiplexing symbols over same frequency band at the same time by exploiting the space dimension in MIMO wireless system is called spatial multiplexing, and this is done because of the SVD tool that we have employed here at the transmitter and the receiver side. SVD is basically decoupling the MIMO channel into T parallel channels to transmit independent information symbols. Thank you.